In Calculus 1, when you start learning about differentiability and the consequences of differentiability, one of the things that you talk about is relative maxima and minima. So you learn that if you have a function like this, then you have, say, this point up here and this point up here are relative maxima, and this point is a relative minimum. I don't care about the endpoints, just so that we don't have to argue about it, let them go to infinity. I don't care. Okay, but I don't care about the endpoints. All I care about is the two red points and the green point. And it turns out that what we want to say, so when you kind of see this in Calc 1, generally the way that this is introduced is that a relative maximum is a place where the function is increasing until that point and then decreasing after. And of course that's true, but that doesn't generalize very nicely to functions of many variables. And so what you have to say is that a relative maximum, okay, so we're going to say, let's give these values names. So let's say A, B, and C. So notice that f of A is a relative maximum. So is a relative maximum since what we have is that f of A is greater than or equal to f of x on some open set containing A. Open sets in the real numbers just refer to intervals with no endpoints. So if I only consider, say, values between here and here, in other words, if I erase the rest of this, I'll put it back in a second, but if I erase the rest of this and consider some, say, open interval here that contains A, this picture is now a little misleading, it looks like, but if I consider just this open set that contains something like that, the A, then here f of A is the largest value over that open set. That's what makes it a relative maximum. There's some open set where f of A is the maximum. Okay, that's when we talk about relative maximums, even going all the way back to Calc 1, that's what we mean. That's what we're going to talk about in calculus. Likewise for relative minimum. So with that in mind, we're going to say that f of W is a relative maximum of f if I did just misspell the word if for your enjoyment here. If there exists a disk, so here it's an open disk centered at W of radius with some radius r, so that f of W in magnitude, the modulus, I mean, of f of W is greater than the modulus of f of z, okay, for all values z in this open set containing W. Okay, so that's what it means to be a relative maximum, is that there's some open set, there's some open disk where f of W is the largest value there. Okay, so that's what it means to be a relative maximum. And you got a relative minimum with the same definition, you just reverse the inequality, right? You got a less than or equal to instead of a greater than or equal to. Okay, so I'm going to basically work everything as far as maxima go, and then analogous statements are going to be true for minimum values, but I'll let you fill in the details there if you'd like. So f of W is a relative maximum if there exists an open disk so that f of W is the largest value on that open disk in modulus. So the modulus of f of W is greater than or equal to the modulus of all the other values. Now, one extra condition that we're going to add to this, we're going to say that f of W is a strong relative maximum. So f of W is a strong relative maximum if f of W is a relative maximum. So if f of W is a relative maximum, and if f is non-constant. Okay, so if you have a function that's going to be constant, then every point is a relative maximum. Here, when we say a strong relative maximum, is that we're just not allowing that situation. So we're not allowing the function to be constant over, over some disk. So to be a strong relative maximum means that you really do have the situation where there's a single point that's larger than all the others, at least locally. Okay, so here, if you just stay with, next to the value a, then f of a is the largest value. There's larger values elsewhere, I don't care, but f of a is a relative maximum. Okay, what I was just saying before is that you can also talk about, if you were to have, say, some function like this, that's constant and then it drops off, say, every value on this set here, okay, every single value, whatever point you pick, would still be a relative maximum because there's some open set that contains that point where that value is going to be the largest value. It's greater than or equal to all the other values. That greater than or equal to is the key. So when we say a strong relative maximum, we're just saying don't let it be constant. It's actually larger than all the other values nearby. So that's what we mean when we say strong relative maximum. And then again, analogously for, I don't know what this word is, but it should be non-constant. Analogously for strong relative minima. Okay, so that's strong relative maximum, strong relative minimum. Okay, I can't spell or I can't type or both, but there we go. So that's what I wanted to say there. So that's a relative maximum and a strong relative maximum. Now, one thing that I want to say here, and we'll call this a proposition. Okay, there's some relationship between harmonic functions and strong relative maxima. So I'm going to try and untangle that as much as I can. There's a lot. We could go really deep here. We could talk about basically harmonic functions and maxima and minima and the consequences and the open mapping theorem and Richet's theorem and Schwarz's lemma, and there's a lot of stuff we could talk about. I'm going to basically just hit the highlights. I'll go a little bit deeper than the book does, but not much. So first, let's talk about some properties that the book lays out. So the first one is that if U is harmonic on a region G, so if U is harmonic on a region, on a connected open set G, then U does not, okay, U does not have a strong relative maximum on G. Okay, so harmonic functions do not have strong relative maxima on G. Nor do they have, so the same is true, do they have strong relative minima. Okay, so that's the first thing. Harmonic functions over a region, over an open connected set, do not have strong relative maxima or strong relative minima. Okay, as a corollary, if f is holomorphic and non-zero, so if f is holomorphic and non-zero on a region G, okay, so on a region G, then the modulus of f does not have, so the modulus of f does not have a strong relative maximum. Okay. Okay, so if f is holomorphic on a region, and non-zero on a region G, then the modulus of f does not have a strong relative maximum. So here is, yeah, so here's the missing piece. Here's the thing that I wanted to add. There's what's called the maximum modulus principle. Okay, maximum modulus principle. And basically what it says is that if you have a holomorphic function, then it's going to attain its maximum and minimum values on the boundary. Okay, so actually let me take one step back before I talk about the maximum modulus principle. There's one thing, and this is related to a homework problem that I gave you, but there's one thing that we need to talk about, and that's the extreme value theorem. Okay, so the extreme value theorem. Okay. The extreme value theorem, so I'll come back and talk about the maximum modulus principle in just a second, but the extreme value theorem says that if f is continuous on a closed and bounded set, so on a closed and bounded set E, then f attains a maximum and minimum value on E. So then f attains a maximum and minimum value on E. So what we mean by that here, and this is actually true of, well, this is true over the complex numbers, this is true over the real numbers, this is true over Rn, it's true over R. If you have a closed and bounded set, closed and bounded sets are in, at least in this context, called compact sets. So if you ever hear someone talk about a compact set in a topological sense, what they mean is a closed and bounded set. And it turns out that f will always reach its maximum and minimum value on E. So just to give you an idea of what this means, so I just want to go back. My intuition, and I assume your intuition, is strongest over kind of Calc 1 land, where we're talking about single valued functions of real numbers. If you were to have, say, a function that's going to look like that. Here's a function that's over some bounded set, but it doesn't have a minimum value and it doesn't have a maximum value because these endpoints are missing. Okay, so those endpoints are missing, so we don't get a maximum, you don't get a minimum. You could likewise talk about, say, the function y equals x over the entire real line. That's a function that's now defined over a closed interval, right? The real line is closed, but it's not bounded. And again, there's no maximum or minimum. But if you have any function that's defined over a closed and bounded interval, so meaning that you include the endpoints, then it's got to reach its maximum or its minimum value somewhere. Okay, so that's the extreme value theorem. The statement is still true for complex numbers or for more general sets. This is actually the theorem that is useful when we were proving the fundamental theorem of algebra, when we were talking about a polynomial. It turns out that not only is f bounded, if you have a closed and bounded set and you have a continuous function defined on this closed and bounded set, then that continuous function is bounded. But actually more than that, this continuous function achieves its maximum and minimum value. So it's not just the scenario where you can have, if you think about the image, that image is also going to be closed and bounded. Okay, so if you start with the closed and bounded interval, then you'll also get a closed and bounded interval, meaning that you'll get another interval with endpoints or something like that. Okay, so this is the extreme value theorem. Now, with that, so in that context, now let's talk about the maximum modulus principle. And what the maximum modulus principle says is that if f is holomorphic, so if f is a holomorphic function, say on a closed and bounded set E, so if f is holomorphic on a closed and bounded set E, then f attains its maximum value. So f attains its maximum value on the boundary of E. Okay, so if you have any holomorphic function over a closed and bounded set E, the largest value that you're going to get from this function will be on the boundary of E. The same is actually true of the minimum. So if you apply the maximum modulus principle to 1 over f, then you get that 1 over f has a maximum on the boundary, therefore f has a minimum on the boundary. So this, again, just like everything else that I've talked about, You can replace the word maximum with minimum, and this is all true. But generally, this is worded as the maxima modulus principle. Okay, so if F is holomorphic on a closed and bounded set, it attains its maximum value on the boundary of E. Okay, so that's the maximum modulus principle.